Hello, everyone. Welcome to the second part of the solving the maze problem using DFS algorithm. We saw that what is the maze and what are the valid moves in the previous video. Now we want to see how we can solve it using the recursion and using this DFS algorithm. So I defined this maze DFS recursion, which I'm passing the starting coordination, the end goal. What is the end goal? Visited metrics and number of moves. So you know that for each recursion algorithm, there should be a base case. If you're not familiar with the recursion, we have a bunch of different videos related to recursion. Please visit them and then come to check this video, because if you don't know what is recursion, you probably cannot understand what I'm doing here. So if in the base case, basically I'm saying if we reach already at the goal that we wanted, then that's it. We solved the problem, right? And then we capture the number of moves, how many moves it took us to start go from the start to the goal, basically. And also we print the result, and also we capture how many solutions so far we found. Because like I said, there is no, if you look at this example, how many paths are from this start to this end? There is one path from here and go all the way down. There is another path that you can go here, then go here, and all the way down. So there are different paths. We want to find all of them and see and keep track of how many solutions we found. And this is the base case. If this happened, we found the solution and that's it, and we return. If not, it means that, okay, first let's go to the right move. So I'm checking if the start 0 basically is the X, start 1 is the Y, coordination of the current position. So when I say Y plus 1, basically I'm saying go one step toward right. And I'm passing this coordination, X and Y, which this Y is updated, moving toward right, and visited is the is keep tracking of which one of the cells we already visited, and I keep track. I copy this visited and update the if this move, if this coordination, next coordination is valid. What I'm doing is um, in the visited cell, I wanted to mark the next move as a true, meaning that we want to visit this cell, and this cell that we want to visit, that the next move, we mark it as a true, so we don't want to visit it again. And if that's the case, then I'm moving the new coordination, which now I'm going to the right, and the goal, which remains the same, and temp visited, which is the copy of the current state of the visited matrix, and number of move plus 1, because we want to move one step towards right. But if this is not correct, so if this is a valid, so we go here, and then we also check what about the left. This was for the right. The left is actually this is up, because I'm keeping the Y, the coordination of the Y of the current position, and I'm increasing the X1 step. So we're going basically one step toward up. This is up. So if we are here, if we keep the Y same and increase the X1 step, it means that I go from this part to here. So this is up. I consider this is up, this is down, this is left, this is right. So I'll check if this move going toward up is valid, then do the similar thing that I did here. I copy the visited, and then I pass it to this recursion function, and then I say number of move, increase the number of move one step, and passing the coordination of the up to the recursion function. Same thing for going up, basically going down, because now I'm keeping the sorry, this is going left basically, because the X is the same. I decrease the value for Y. So it means we're going left, because imagine if you're here and the x is the same, and we go one step below. So it means that one step to the left. So it means we go here. So this is moving. That's why the coordination of y, this is the y coordination of the current position is -1. I put it here. So, and then do the similar thing that I did for the previous ones. So copy the visited, update the left cell as a true, because we will visit that, and then pass everything to the maze recursion function to start again with moving left. And then for moving up, basically, or in our case it would be moving down, because I keep the y the same, and I decrease the value for x, which means y remain the same and decrease the value for x. So it means if we are here, we go here, which in our case is down, because I considered here down, here up. And do the similar thing, and then yeah, that's it for the recursion. Now we want to run it, right? So I said at the beginning, we are at the 0, 0. We want to start from here. Start at here, and then the goal is, so this is the starting point, this is the end goal, or the destination. This is the visited, which at the beginning every cell in the visited was false, and then this is the number of count, how many moves so far we have. So we basically, I put this cell 0, 0 through, which means we are already at index 0, 0. And then we run this and tell us how many steps we have. Okay. I just ignore this. It's not. So let me run this now. And these are the solutions that we have. Let me copy them so we can. Oops. Give me a second. All right, so let me copy them in the separate document here. All right, so let's see, how can we evaluate this? If we all right, so let me bring that up again. All right, so this one, it says that with number of, you see the ones here, ones is the path that this robot took at that move. So it says, all right, at the first move, this is the first solution that he hits. It says with 8 moves, I can reach from this here to here. And it says go all the way right and go all the way down. You can check it, right? So if you go all the way right and down, you will reach here. And with 8 move, 14 move is going all the way right, then down, left. This is like this path. So it's go all the way here and go this path, and so on and so forth. For example, this one is 10 moves, right? So it says go here and there. So basically, it goes here, 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 all the way there. And in total, we have 10 solutions for this. Okay. So just for showing you that this can be anything you want, let me change this to example. Let's say this, right? So it means, let's say I create an obstacle here. So the path from here should no longer exist for us. So if I run this one more time, and now you see it says number of solution is 5. So it means it got rid of the sum of the solutions that it was including this cell, because this cell is no longer valid cell. So if I copy this now, let me put it here. Let me delete this. All right, so what it says, this path is still valid. This one is still valid with 14 move. Actually, it's 8 move. I didn't copy this part. So now this part is still valid because it's going beyond this. And if you see none of this solution, consider this 0 here, because this cell we now consider it as a 0 comparing to the previous solution. So that's it for today. I will create another I'll probably explain this a little bit in the next video, and I try to solve this maze using another method, which is not using recursion. It's like using the stacks in the Python program. So stay tuned for the next solution, and leave down below if you have any question or comment. Have a great day.